This is number 8 from the AP Live worksheet. We have a piecewise function here. Function f is defined on all real numbers such that f of x is x squared plus kx minus 3 for values less than or equal to 1, and 3x plus b for graphs to the right of 1. For which of the following values of k and b will the function f be both continuous and differentiable on this entire domain? So we know that these two branches of graph are defined in different locations, but what we really want to care about, what we want to help us figure out k is we know that these branches of graph are going to intersect or are going to connect in a very specific way. First off, it's going to be continuous, meaning that this graph will lead to this graph. Okay, they're going to touch at x equals 1. So they must have the same y value. Because they're continuous, we know that these two equations, they must be equal to each other at x equals 1. At x equals 1, they must share the same y value. So we have something that we can work off of. Something else, though, is that it's also differentiable. So not only are they meeting at the same y value, they're meeting in a way where the graph is going to transition nicely in terms of slope. So that means the slope of these two graphs are also going to be the same value at x equals 1. So that's another equation that we can set. We can find the derivatives of these, set the derivatives equal to each other, because we know that they must share the same derivative value, or they must share the same slope. So we have two equations that we can set. We have the original equations we can set equal to each other. X squared plus kx minus 3 is equal to 3x plus b. We also can find each of their derivatives and set them equal to each other. So x squared plus kx minus 3, the derivative of x squared becomes 2x. Kx becomes k, and 3 drops out. And then the 3x plus b's derivative, 3x becomes 3, b drops out. So now I'm going to set the two equations equal to each other. Replace my x with 1. So I get 1 squared plus k times 1 minus 3 is equal to 3 plus b. Combine like terms, I'm left with k minus 2 is equal to 3 plus b. And that's maybe as far as I can go. We can combine the 3 and 2 together, but we're not going to be able to solve for k or b. So we need something else. And that's where the second derivative is going to, or second equation is going to help us out. We'll set the derivatives of each function equal to each other. So 2x plus k is equal to 3. Replace x with 1. So 2 times 1 plus k equals 3. K equals 1. Now let's plug k, replace k with 1, and that will give us the ability to now solve for b. Okay. So 1 minus 2 is negative 1. Minus 3 is negative 4, so b equals negative 4. Number 9, we have y is equal to e to the kx. The k is a coefficient, it's a numeric value. X is the variable here. We want to find the fifth derivative. Okay. So let's start off with e to the kx. Remember that the derivative rule for e to the u is e to the u times u prime. So e to the kx becomes e to the kx times k, right? Just like how we would find the derivative of e to the 3x. We would say e to the 3x times 3. So e to the kx times k. So this k is a coefficient. It's just going to hang out in front. We're going to find the second derivative. Again, the coefficient is, there's no need for product rule. Coefficient will just kind of hang out in front of the derivative. So e to the kx becomes e to the kx times k. So each time we find the derivative, another k is going to pop up. So third derivative, e to the kx times k with k squared in front becomes k cubed. Fourth derivative, e to the kx times k with k cubed in front becomes k to the fourth. Find the derivative again. This e to the kx will produce another k, and that's going to sum the k up to be k to the fifth. Number 10, consider our function 6x over a plus x cubed. Find the value of a given that f prime of 0 is equal to 3. So if we can find the derivative, then we can use this to plug in for x and y, and then we can solve for a. Now I see that this relationship is numerator over denominator. I have to go through quotient rule. So f prime g minus f g prime all over g squared. So 6x's derivative becomes 6. The original g function minus the original f function, g prime, so 3x squared, a plus x cubed becomes 0 plus 3x squared, so a is it's a numeric value, constant, goes away to 0, all over denominator squared. So now I have my derivative. I know this order pair can be used inside my derivative equation, so 3 will plug in for f prime of 0, replace every x with 0. We get 6 times a plus 0 cubed. All this will go away to 0. So we get 6a minus 0 over a squared equals 3. Cross multiply, we get 3a squared is equal to 6a. Subtract 6a from both sides and factor out the 3a. We get 3a times a minus 2 is equal to 0. So a is equal to 0 and a is equal to 2. Okay, number 11. We have positive variables b and h change with respect to time t, so that's a hint that we're going to have to go through related rates here. So again, related rates says we're going to find the derivative like we normally would. Every variable gets affected, but we have to involve d over dt for each of those variables because time is the independent variable. Okay, the relationship between b and h is given by the equation h cubed is equal to 4 minus 2b quantity squared. At the instant when db over dt equals 3 and h equals 4, what is the value of dh dt? Now, we know that if we want to involve db dt and dh dt, we're going to find the derivative. So let's go ahead and do that. So here's my original equation. Go through power rule. H cubed becomes 3h squared, but we need to attach dh dt. This is a chain rule here, so we do the outside function's derivative, bring down the 2, keep the parentheses, subtract 1 from the exponent, multiply by the inside function's derivative, so 4 goes away, negative 2b becomes negative 2 db dt. So now let's see what we can plug in. db dt gets replaced with 3, h gets replaced with 4. We want to find dh dt, but there's still this b that's sticking out that we don't know what that value is. It's not given to us, or at least not explicitly. So let's see, is there a way that we can find b given what we have? So maybe not with this equation, but maybe with the original equation, right? We know that h equals 4, so we can use the original equation to help us find the b value at that moment in time. So back to the original equation. Let's plug 4 in for h, and let's solve for b. So 4 cubed is 64. We take the square root of both sides because we want to solve for b. We want to release that b out from under that parentheses. So we get 64. Square root of 64 is 8, or plus or minus 8 rather, because of the equation. And then when we solve for b, we know our b has to be a positive value, a positive variable here. So 8 equals 4 minus b. If it's positive 8, I'm going to get b equals negative 2, so that's not going to work. If I let negative 8 equal to 4 minus b, I'm now able to subtract 4, divide by negative 2, I get b equals 6. So now I have the b value needed to help me work towards solving for dh dt. So b gets replaced with 6, h gets replaced with 4, db dt gets replaced with 3, so now the only variable that I'm left to solve is dh dt. So 3 times 16 is 48. Multiply all this out, 2 times negative 8 times negative 6, we get 96. So divide both sides by 48, and we get dh dt equals 2. All right, number 12, again, this is related rates. We see dz dt. We know that z equals xy squared. We have all these values given to us, and we want to find dz dt. So first up, I know I got to do related rates, but there's also product rule involved here because we have two variables that are being multiplied with one another, right? So we have to go through product rule. F prime g plus f g prime. So x becomes dx dt, g stays, f stays, and then g prime, y squared becomes 2y dy dt. So let's see what we have. We have dx dt, which is -2. We have y squared. Well, actually, we have y, which is 1/2 squared. Plus, we don't have x. We have y, and we have dy dt. So we have two missing variables. We need to figure out what x is. So let's go back to the original equation. Maybe this can help us out. We have z, we have y, and we can use that to help us solve for x. So replace z with 3, replace y with 1/2, and now we can solve for x. Multiply both sides by 4, we get x equals 12. Okay. So now when we plug 12 in, we're able to get this down to -1/2 plus 60 equals 59.5, or 119/2. Okay, number 13, approximate value of y is equal to the square root of 3 plus e to the x at x equals 0.08 obtained from the tangent line to the graph at x equals 0 is. So we're going to apply steps for linear approximation. Okay, so let's go through the steps for linear approximation. First, you want to find the ordered pair at x equals 0. Second, we need slope, so we're going to find the derivative, find y prime, and evaluate the slope at y prime of x at 0. And then we have ordered pair, we have slope, we can put it in point slope form, and once we have our linear equation in point slope form, we can plug that decimal 0.08 in for x. Okay. Alright, so to find ordered pair, we'll plug 0 into the original function. We get root 3 plus e to the 0, which is 3 plus 1, which is root 4, which is 2. Ordered pair is 0, 2. So next we have to find the derivative so we can find the slope. So let's get this ready for chain rule. Rewrite this as parentheses to the 1/2. Bring the 1/2 down. Subtract 1 from the exponent. Multiply by the inside function's derivative. We have our derivative. We can now plug 0 in for all the x's. So 3 plus 1 is 4. Square root of 4 is 2. We have to flip that to be 1/2. Sorry, 1 over root 4. So root 4 is 2. 2 times 2 is 4, is 1/4. We have our slope being 1/4. So now we have our ordered pair. We have our slope. Put into point slope form. Get y by itself. And now our final step is where the approximation comes in. We're going to take that 0.08 and put it into the linear function. 1/4 times 0.08 is 2. Is 0.02. 0.02 plus 2 is 2.02. Okay, number 14. We have a function c of x that gives the dollar cost of digging a hole x feet deep. So this x represents how deep that hole is, and then whatever c of x gives us, that's going to represent the dollar cost. So c of 20 equals 140. That means a hole that is 20 feet deep is going to cost $140 to dig. All right. C prime of 20 is equal to 5. That means the rate of change at 20, that means when the hole is 20 feet deep, the rate of change, the cost of digging is increasing, okay, at a rate of $5 per foot. So the positive is going to represent something. It's the fact that it's increasing, and it's a rate of $5 per foot.